Craig, thank you for the invitation, of course. I'm very happy to talk to you via Zoom. Today I'm presenting a preliminary work actually, because it has primarily been done in the framework of a new proposal, but partially also in the framework of the NASA Sea Level Science team. And I'm talking about the probabilistic reconstruction of global and regional sea level rise and individual contributors over the 20th century. So yeah, let's have a look at what is available today. Nowadays, we have a modern remote sensing observation system that allows us to track very accurately global mean sea level with satellite altimetry. The satellite altimetry record is shown in the lower left plot in black from 1992 to, in this case, I think 2018. The good thing with satellite altimetry is that it measures sea surface haze at a near global scale with a very high precision, and it allows us to determine global mean sea level very accurately. However, over the last 18 years, we have also been able to track the individual contributors of sea level change with different measurement systems. For instance, we are nowadays able to track with GRACE and GRACE follow-on barystatic mass changes in the ocean. Barystatic mass comprises everything, including melting of glaciers, ice sheets, and land water storage. And the corresponding record is shown here in the lower left in blue. And you can see that it explains quite a bit of the global mean sea level trend, but also a lot of the temporal variability. We also have, since now 2004, I think, the Argo network in place. Argo is a program which consists of floats measuring temperature, salinity, and pressure in the oceans that allows us to determine spheric expansion. And the resulting record is shown in the left plot in red. So if we add both contributions, the spheric expansion and the barystatic mass changes together, then we get the magenta curve. And you can see that it fits very well the observations from satellite altimetry, suggesting, first of all, that the measurement systems actually work very well. And the second thing is that now we have a very good understanding of global mean sea level changes over that particular period. However, if you look at regional scales, and particularly before that modern remote sensing system has been in place, before 2004 or 1993, sea level is generally much less well understood. And there are a few reasons for that. The first is that when we look at regional scales, we have additional processes that affect sea level locally. First of all, we have stereodynamic sea level changes, and that comprises everything of local spheric expansion, ocean circulation changes, or atmospheric wind and pressure forcing, redistributing heat, salt, and mass in the oceans. And the second reason is that any barystatic mass change, for instance, due to a melting ice sheet, does not only add sea level uniformly around the world, but it induces a very unique geometry due to gravitational, rotational, and deformational processes, which effectively results in very low sea level rates or negative sea level rates around a melt source and increases in the far field. And as a result, we get a very unique geometry in sea level as well. And this can be seen when looking at satellite altimetry trends relative to the global mean. So the global mean has been removed in this map from satellite altimetry. And you can see that there are areas of increase. These are the reddish areas, and other areas which are blue. And you can see that sea level rates vary, or linear rates vary over that particular period by plus minus 6 millimeters per year. So there's a lot of variability, making it much more difficult to actually understand what's going on. The second issue with is that before 1993, we only have tide gauges measuring sea level relative to the land along the world's coastline. And in this plot here, it shows again the linear rates from satellite altimetry since 1993 relative to the global mean. But now overlaid are shown the same linear trends from the tide gauge network, shown with these little dots. And you can see that while many of those dots agree with satellite altimetry in the surroundings, and many others do not. And the problem is here that tide gauges measure actually a different process. They measure relative sea level. So they not only measure the sea surface height change, but they also measure any variations of the land on which they are grounded, which we call vertical land motion. And there are two different reasons for vertical land motion. The first is a natural one. It's glacial isostatic adjustment. It's in principle the same process as we just explained for contemporary mass changes, but it is related to the melting of the last ice age in the large ice sheets during the last ice age. And this can be seen, for instance, in this blue rectangle over Scandinavia, inducing nowadays still a rebound, so an uplift in that region, leading to relative sea level falls, outpacing the sea level changes that we see in the ocean. The other reason for the vertical land motion are anthropogenic causes, for instance, fluid withdrawals, for instance, due to gas extraction or groundwater withdrawal. And the red rectangle marks a region where these kind of variations have been very dominant. In the Gulf of Mexico, for instance, there has been a lot of fluid withdrawal, and you see that in the linear trends from the tide gauges, which are much larger there than from satellite altimetry over the same period. So all in all, that makes clear that it becomes very, very difficult to actually estimate the geometry of sea level change from that sparse tide gauge network, in particular, considering that it is also measuring additional processes. And it is therefore very clear that we need very sophisticated and ideally probabilistic frameworks that not only take into account the tide gauges itself, but also any prior information that we have on these processes. And that's what I want to present today. I want to present an updated reconstruction of 20th century global mean sea level change, including individual budget components using the Kalman Smoother framework, which has been introduced by Carling Hay in 2015. And the second goal is to evaluate the budgets along the coast at individual tide gauge sites. So, as I said, the Kalman Smoother approach we are using is based on Carling's approach from 2015. A Kalman Smoother, very briefly, is a probabilistic state estimate that uses both observations and models to predict a dynamical system. As observations, it uses tide gauges, of course, but it also includes prior information, and I think that was a fantastic new thing introduced by Carling. So it introduces prior information that we have on different processes, for instance, glacial isostatic adjustment or stereodynamic ocean models, and different ice melt fingerprints. In the 2015 version from Carling, she actually used 161 different GIA models that use different parameters based on Peltier's GIA models. It also used the ocean component of 6 CMIP5 ocean models, and it used static ice melt fingerprints. So they didn't use any temporal information, but they used the static ice melt fingerprints from different sources that were fitted to the tide gauge, and then the amplitude was estimated for every individual melt source at every time step, considering the other processes at work as well. The evaluation works then, there's always one combination of one GIA model, one ocean model, and a fitted fingerprint that is assessed, and the residuals to the observations are then used to estimate the most probable combination and estimate global mean sea level. So let's look into the results. As a result, they got the first probabilistic global mean sea level estimate at that time, which was significantly lower, in particular before the altimetry period than previous estimates. It also allowed to decently predict regional sea level changes. And this can be seen in the plot in the lower left. Here I plotted for a number of very long tide gauges that are commonly used when assessing 20th century regional sea level changes. So it shows the linear trends over the entire period since 1900. These are the black dots with the error bars surrounding it. And then I also plotted from the nearest neighboring location the estimate of the Kalman Smoother. And you can see that it decently fitted the regional variability seen in these linear trends, though there are still some differences remaining. An important thing to consider in that form of framework is that the different ice melt fingerprints have a very large covariability, so they are highly correlated with each other. Maybe I go back to the slide before. On the lower left, you can see two different fingerprints. The upper one shows a fingerprint of the Greenland ice sheet, and the right one shows a fingerprint from Iceland. And you can see that both fingerprints look very, very similar. So they are hardly distinguishable, meaning that they are very highly correlated. And in this paper, in the first step, or in the development of that framework, the goal was to estimate not only total sea level change, but also the individual contributors. And because of that correlation of these fingerprints, that was not possible at that time. They were able to accurately or robustly estimate the total sum of all contributions, but they couldn't really distinguish between individual melt sources or mass changes and spheric expansion. And this is actually—
Sönke, can I interrupt you? Sorry, I hope you don't mind. I should have asked you earlier on if you mind if we interrupt you with questions. We have a question in the chat from Vivian. Vivian, would you like to unmute to ask your question quickly?
Oh no, it was just a passing comment because, you know, when he mentioned all the different causes of vertical land motion, he didn't mention the tectonic forces, you know, particularly along the Pacific. That was simply a side comment.
Yes,
Okay,
absolutely.
yeah.
That's absolutely correct. Yes, thank you for that.
Sorry.
Yeah, so our goal in this presentation on this project was to update that Kalman Smoother. So we used the same framework, but we wanted to improve on the representation of regional sea level changes, and in particular the different budget components. And the main thing since that paper from Carling in 2015, or the original paper from 2013, there have been a number of different new estimates of barystatic mass changes become available. In particular, most of those mass estimates have been summarized in a paper by Thomas Fredericks and colleagues in 2020, where they looked at the global sea level budget since 1900. In these estimates, they produce a large ensemble of 5,000 different members containing all the different ice melt contributions over the 20th century, but also terrestrial water storage. We wanted to use that ensemble. Here we used the 100 representative 100-member ensemble from Frederiksen and colleagues to pre-describe the ice melt sources instead of only using the static fingerprint. So we include the temporal information, and therefore we avoid the covariances between individual fingerprints. We also changed the GIA models. We used 6 commonly used GIA models that have been used in the sea level community before. And another adjustment that we did, instead of using CMIP5 ocean models, we now use ocean reanalysis. The advantage here is that in ocean reanalysis, observations of temperature and salinity are assimilated, so they represent the real state of the ocean or the observational state, providing a little bit more accurate information than a CMIP model, which is not representing the real variability in the system. The evaluation is then in principle the same, only with the difference that we are not directly estimating only global mean sea level change, but rather global mean spheric sea level change. That is then in that moment entirely based on tide gauges. And we also get estimates of the different budget components, so the mass change and local spherodynamic sea level changes. And that allows us then to estimate the regional sea level change, including all different budget components. Yeah, let's move into the results. Here shown again on the right side are again the regional sea level trends from satellite altimetry relative to the global mean. We have seen that map before. And in the lower part, we can see the same map, but now based on the Kalman Smoother framework. So based on tide gauges and prior information. And you can see that in principle, the two maps look very similar. So you see the same regional patterns. Bluish areas are usually in satellite altimetry are usually also blue in the Kalman Smoother estimates, and reddish area as well, red in the Kalman Smoother framework. And this becomes visible if we look actually in the pattern correlation, which is approximately 0.6. So that shows that they fit relatively well. We also get with the framework a new updated global mean sea level curve since 1900. This is shown now in blue in comparison to the estimate from satellite altimetry in black. And you can see that both agree very well. And over the 20th century, this new curve has a linear trend of 1.5 millimeters per year, which is in very good agreement to former estimates. But the new thing in our updated assessment is now that we not only can estimate global mean sea level change itself, but we can also estimate the individual contributing factors in terms of barystatic mass changes. And we get a new tide gauge based spheric global mean spheric estimate, which is shown in red in this new map. So instead of only having global mean sea level, we now can also assess the individual contributing factors. The shadings always indicate the uncertainties that are estimated within this probabilistic framework. So we can also look into the rates of change shown now on the red plot. Again, in black, global mean sea level, in blue, barystatic mass changes, and in red, global mean spheric sea level changes. Overlaid shown are also in green with the error bars, the rates from a recent estimate of global mean spheric sea level change from hydrographic profiles and from ARGO. This was published by Chen and colleagues in 2017 in Nature Climate Change. And we used that just to validate our estimate, which is now solely based on tide gauges. And you can see the red and the green curves agree very well, both in terms of the linear long-term trend, but also in terms of these non-linear variations that we see in the rates. Most importantly, we see that the global mean sea level curve shows as former estimates an acceleration that has been initiated at the end of the 1960s. In the different budget components, we now also see that it has been initiated by primarily spheric expansion at the end of the 1960s. And over the last decades, the global mass, the barystatic mass contributions kicked in as well, leading to a very persistent acceleration in global mean sea level since the 1960s. We can now also investigate that new estimate regionally using, again, different tide gauges. Again, this is a selection of tide gauges that is commonly used to assess regional sea level changes over the 20th century because they are particularly long. It's a plot that I showed before already. In black again, shown are the linear trends for these tide gauges. In red, we can see the estimate based on the framework from Carling Hay from 2015, and in yellow now our updated estimate. And the main message is here that you can see that we get now a better fit to the existing tide gauges than with the previous framework. And this is primarily related to the fact that we now include these different observation-based ice mass contributions. But we can still see that at some locations, for instance, here in San Diego, there are still differences to the observations, and I will come back to these differences in a few minutes. We can also we can actually look at those differences between tide gauges and the Kalman Smoother estimate at individual tide gauges at a global scale. And this is done in this next plot. So we estimated for every individual tide gauge location around the world since 1900 over the available period, a linear trend. For the tide gauge itself, but then also for the nearest neighbor grid point from the Kalman Smoother reconstruction. And in the map on the left side, you can see the differences between these two linear trends. And on the right side, you can see a scatter plot between the two estimates. In the scatter plot, you can see that there's a reasonable good agreement between observed linear trends and reconstructed linear trends, which results in a correlation of 0.6 and an RMSE of 1.8 millimeters per year. In the map, you can actually see how these differences between the two products are distributed around the world. And you can see that the magnitude of those differences is usually in the order of plus minus 3 millimeters, or up to plus minus 3 millimeters. You see, for instance, here in the Gulf of Mexico, these large differences that are even larger than 3 millimeters per year. So it's a good fit, but it's not a perfect fit. And I want to emphasize that we shouldn't expect a perfect fit, because in the Kalman Smoother, to remind you, we included a few processes, including GIA, zero dynamic sea level changes, and barystatic sea level changes. But we didn't include directly an estimate of other vertical land motion, for instance, due to these tectonic influences or due to groundwater depletion. So there's a number of different processes that have not been included because they can't be modeled at a global scale yet. So the question is, are the differences that we now see in this map, are they related to these residual processes? The good thing is we nowadays have a GNSS network or GPS network available that measures vertical land motion at or near tide gauge stations, and those can provide residual vertical land motion information as well. So we actually looked into these residual vertical land motion estimates. Here we use estimates that have been published in the same paper from Thomas Fredericks and colleagues in 2020. and try to remove residual vertical land motion from the tide gauges and then reassess the differences to the Kalman Smoother framework. Again, the same plot. In the scatter plot, you can see now if we account for residual vertical land motion at tide gauges, then the correlation increases to 0.9 and the RMS E decreases to 1.2 millimeters per year. And you see that many of the differences on the map that were, for instance, dark red before, like in the Gulf of Mexico, become now become lighter. So the differences become smaller than in the previous estimate, and the accuracy increases. And this suggests that indeed many of the residuals can be explained by processes that have not been accounted yet. But it also means that we get a very accurate estimate of the other components and that we can solve the budget locally within the error bars. Before actually looking into an example budget at a tide gauges, I would like to explain you an issue that we have with solving local sea level budgets before. When looking at the sea level budget, so explaining the individual contributions at a local tide gauge along the coast, we always had the problem before that our observation system was not comprehensive enough to actually do that. And the problem was that while globally we can estimate temperature and salinity in the ocean, integrate it over depth and calculate the global mean spheric sea level change, but that doesn't hold locally because it is defined as in depth integrated spheric expansion. And when we would estimate that at a local tide gauge on a shallow shelf, that would be essentially zero. So what we observe at a tide gauge is actually not only the local spheric expansion, but primarily ocean circulation changes, so mass changes that result from spheric expansion somewhere else in the ocean. And to estimate the local budget in previous attempts, we always had to go somewhere off the continental shelf into the deep ocean, estimate spheric expansion there and try to relate it to a tide gauge, which comes with its own difficulties. We had a paper on that last year where we tried to actually develop a framework to assess those at a near global scale. But this is one of the biggest challenges that we had with local budgets. The good thing now with the Kalman Smoother framework is that the Kalman Smoother framework overcomes this issue by integrating ocean circulation changes assimilated by climate models and ocean reanalysis into the whole system. So rather than going somewhere into the open ocean and estimate spheric expansion and trying to compare that to a local tide gauge in a budget assessment, it actually takes these observations and an ocean model and models the ocean circulation with the physical understanding that we have about the processes. And here in the Kalman filter framework, these ocean models are integrated. So we get an estimate of local aerodynamic sea level change as well. And how well that works is illustrated here for the tide gauge of Cuxhaven in the North Sea in Northern Europe. In blue, we can see the observed tide gauge record. And then in gray, we see again the estimate of the Kalman Smoother budget. And you can see that both the trend and the variability are very well reconstructed by the Kalman Smoother framework, resulting in a correlation of 0.9. But in addition to that direct sea level estimate at that location, we now also get the individual contributions in terms of aerodynamic sea level changes. They are now shown in red. We can also we also get the barystatic GRD processes, the mass contribution locally, and the different the GRA estimate. And we can now use these processes and explain everything at a local scale as well, which is definitely a step forward into the right direction. Last but not least, I want to talk about further application. As I mentioned before, with the Kalman Smoother framework, we are now able to estimate sea level changes even locally relatively accurate. And as you have seen in the plots before, the remaining differences to local tide gauges were indicative of vertical land motion changes that have not been directly included into the Kalman Smoother framework. So we could also think about the Kalman Smoother results and take those results to actually estimate vertical land motion on a time scale of centuries. To give you a brief introduction to that, nowadays we can estimate vertical land motion with GNSS from space, but usually these estimates are only available over a few years to maybe 2 decades or something. So they are usually just covering the very recent years, and they are not representative of the entire 20th century. So they are usually used as linear estimates that are extrapolated into the past and also into the future. So if we use the Kalman Smoother framework and estimate the difference between the Kalman Smoother estimate and the nearby tide gauge station, then we could also interpret it in terms of vertical land motion over that period, including potential nonlinearities. Nonlinearities can be expected at many locations, for instance, due to groundwater withdrawal or any other fluid withdrawal, which has not been linear over the 20th century. The other technique that has been used in the past to estimate vertical land motion has been tide gauge minus nearby satellite altimetry. So this is very similar to what we want to do now with the Kalman Smoother, because tide gauges measure, as I said already, sea level relative to the land on which it is grounded. Satellite altimetry measures sea surface height, or real sea surface height. And the difference between the two should usually be vertical land motion or any other process that is not really resolved by satellite altimetry. And that technique has been used before in addition to GPS or GNSS estimates to assess vertical land motion at tide gauges. So we now use the Kalman Smoother framework to do that. And in the left plot, you can see a comparison of our estimates of vertical land motion or to the estimates that we get from tide gauge minus altimetry. And you can see that we get a correlation between the two in the order of 0.91. So there's a very good agreement between the two different products. Not shown, but already undertaken, has been a similar comparison to the GNSS network at those tide gauges. And we come up with an even slightly larger correlation and an accuracy that is in the order of 1.2 millimeters per year on a global scale. But the real advantage, as I mentioned before, is that we can now go much farther back in time and get estimates that extend over the entire 20th century. And this is illustrated in 2 examples for Manila on the Philippines and Galveston in Texas in the 2 plots below. Again, in blue, you can see the observed tide gauge sea level, relative sea level, and then in black, the next grid point estimate from the Kalman Smoother. And you can see that both do not agree. For instance, in Manila, both agree very well up to approximately 1960, but then relative sea level at the tide gauge increases extremely up to today, while the Kalman Smoother increases as well, but with a much lower pace. So if we look at the differences, then we could use, we can interpret those differences in terms of vertical land motion or any other processes, nearshore processes that are not necessarily resolved by by, for instance, satellite altimetry or the ocean models that we used in this framework. Also, this is shown in red from the Kalman Smoother, and in yellow overlaid the same estimate from the common technique of tide gauge minus satellite altimetry. And you can see again in these two examples, the two estimates agree very well, not only in terms of the trend that is observed, but also in terms of the variability. And more importantly, you can see that we get those estimates now over the very long time period, including these nonlinearities that we know very well in Manila. The same for the Gulf of Mexico and Galveston. You can see that the increase is not linear. There are some periods like in the mid 20th century where there are rates that are a little bit faster and then slower at the end of the 20th century again. And this has been seen in other assessments as well. So this is an ongoing project that we currently do within the framework of the NASA sea level change team. And we hope that we can get those estimates at a global scale at tide gauges, over the entire 20th century.
Can I interrupt you again? Sorry, we've got a couple of questions. One from Christopher, who I would like to ask his question, and then Stephen.
Yes.
Yeah, Sönke, I'm curious about this plot. The first figure you showed on the left, this is a really strong agreement between tide gauge minus Kalman Smoother and tide gauge minus altimetry. But I wasn't sure if I was supposed to be interpreting this as something like an independent comparison, because if I remember right, you're using all these ocean reanalysis products, and many of them assimilate altimetry data. So I'm wondering if I shouldn't be interpreting this as an independent comparison.
Yeah. That's probably okay. I mean, not all of those, I think, actually assimilate satellite altimetry. That depends a little bit on the products. There's something I need to check. But as I said, I did a similar comparison, unfortunately not shown here, but with a GNSS, which is definitely independent, and that shows even a better agreement.
Okay.
So these are the two. Unfortunately, these are the two only types of information that we can integrate at a global scale currently. But we are definitely trying to get other independent estimates that can further increase the evidence that we are really estimating vertical land motion with the residuals.
Sure, thanks.
Thanks for the middle figure. I'm looking at Manila, and in 1960 you get a big VLM signal. Is that anthropogenic?
We have to look into the details yet, so I can only refer to the literature that exists. So this is primarily related to groundwater depletion. So yes, it is anthropogenic.
Okay, thank you.
Further questions?
I think that's it for now. Thanks everyone.
Okay, thank you. But I think I can already sum up some take-home messages. The sparsity of sea level observations in terms of tide gauges, hydrographic data, etc., hampers a proper estimation of global and regional sea level and its budget, particularly along the coast. Here we have reformulated the Kalman Smoother that has been introduced by Carling Hay in 2015 with prior information of observed ice melt fingerprints and ocean reanalysis, which allows us now for an improved assessment of the 20th century sea level budget, both globally and regionally. And our new global mean sea level estimate is in pretty good agreement with former assessments, 1.5 millimeter per year over the 1900 to 2018 period. So nothing new. It also shows a significant acceleration that has been initiated in the 1960s. But in the framework, we get evidence for steric expansion being responsible for the initiation. This acceleration has been further increased later at the end of the 20th century and in the early 2000s by barystatic mass changes. This is actually something that we really have to take into account. As you all probably know, barystatic mass changes or ice melt, in particular the ice sheets in Greenland and Antarctica, they contain the largest sea level equivalent, so they bear the largest potential risk for the future. And it's really a worrying sign that barystatic mass changes are now the dominating factor in terms of the acceleration in global sea level. Furthermore, we have shown that when we compare our new estimates based on the Kalman Smoother framework with nearby tide gauges, it allows us for the detection of unmodeled processes, for instance, VLM. And we hope that within our NASA sea level change project, that we can come up with nonlinear estimates of vertical land motion that cover the entire 20th century. So there's a lot of work that needs to be done to actually link those nonlinearities that we see in these differences to certain processes and increase the evidence that we are really getting vertical land motion and not anything else. So with that, I would like to thank you for your attention and look forward to your questions. And here's just a list of a few references, if you like, to read more details, for instance, on the approaches and all that stuff. Thank you.
Thanks so much, Sönke. Fascinating. I see it's happening virtually. We have a question in the chat from Gavin, so I'm going to ask him to please go ahead.
Mm-hmm. Hi, yeah, great talk. Yeah, one of the things obviously is that VLM is very, very local. I mean, if you look at some of the INSAR data, you see, dramatic changes, block by block by block, right? So any particular tide gauge really needs very, very local VLM data to correct it. I'm a little confused as to why you're trying to predict the VLM affected tide gauges as opposed to correcting the tide gauges and only using VLM corrected tide gauge data in this whole big system for the attribution. And then if you want to make a prediction for what's going on locally, you would put the VLM back in for the based on local processes and local issues. Right? Why is all the VLM stuff getting into the Kalman mechanisms and toolkit?
Yeah, thank you, Gavin, for that. Yeah, the first thing is you're absolutely right. This is definitely a test that we want to do to actually correct the tide gauges before using the Kalman Smoother framework. I have to say that in the Kalman Smoother framework, there's no prior information on vertical land motion included, but the framework allows for local processes at tide gauges that are then not part of the global sea level field itself. The main motivation of not using the GPS records, for instance, is that they cover only a very short period of time, and much of the vertical land motion is not linear. So if we assume that it is linear over the last, let's say, 10 years, that is not representative of what happened over the entire 20th century. And the goal here is really to, at least in the NASA project, to estimate nonlinearities from the tide gauge network itself. So we hope that the Kalman Smoother framework with that prior information is intelligent enough to estimate those. So that's the main driving factor behind that assessment.
Thanks.
Thank you.
Thank you, Gavin. Next, we have Christopher. I see has his hand up.
Thanks, Craig. Yeah, so Gavin's question made me think of another related question Sönke. And I'm wondering, so Gavin's question and also one of the figures you showed, how to pose this question. What does your model framework assume about the space and time scales of the residuals? You would think that, you know, if you regard, so similar to what Gavin was asking, if you regard these sort of large local sort of VLM signals as residual, if you want to predict that in the absence of data, you've got to make sure that you're modeling the spatial and temporal scales appropriately. And yeah, so I guess my question is, what does your model assume about the space-time structure of the residuals, and does a residual analysis of the model solutions confirm that those assumptions are appropriate?
I haven't looked too much into the details. I'm using the original framework, and I think in the original framework, the spatial covariance function is used to determine this residual function, with, I think, a length scale of 500 kilometers or something.
And what is it? Do you know what it assumes about the time scales? I'm thinking about that Jakarta time series that Gavin was pointing out, and yeah, you know, it has this very sort of, it has the obvious inflection point. I'm wondering if the temporal structure of the residuals could model something like that.
Difficult question. Definitely something that we could assess further.
Yeah,
but I have no immediate answer to it.
Yeah, well, I think, you know, I think something that comes to mind. So I mean, the issue is a prediction one, right? You want to have confidence in your algorithm to predict things you don't observe. And so, you know, one way to get at this, you know, you showed a lot of very high R values. I'm wondering if you've played around and done something like, I guess you could call it cross-validation or data withholding experiments. I mean, really quantifying what the prediction error in your model is, like sort of, you know, withhold something like a quarter of your tide gauge records, get your solution, and then compare, see if your solution can predict those data points and sort of quantify, you know, what the prediction error is associated with that. I think that would give you a direct sense of to what extent your model is doing what you hope it does in complicated cases like that. And I think that could inform, you know, questions like Gavin's.
Yeah, that's a very good point, and it reminds me actually. I have done some initial experiments with climate models, actually, where I pre-describe, or I used a climate model to test the whole framework, and I included random vertical land motion estimates based on observations into that model world, and try to predict the sea level changes and vertical land motion with the Kalman Smoother framework. But the results are very preliminary. So I did them for one climate model or something. If I remember correctly, the accuracy was in a similar order as we saw from the comparison to GNSS. So in an order of 1.2, 1.3 millimeter per year or something. Okay, cool. But I haven't looked into the non-linearities there. So this is really, really preliminary.
So that, I mean, so that's really neat. And I think so. So what you've just described there is something more like a perfect model experiment, which is super informative. Yes. And so what I'm suggesting would be like a cool pairing to that, right? Because you're playing around in model world there, where you kind of know the truth and you sort of simplify things, and that's really instructive and informative. And I think if you took that and paired that with something like this cross-validation exercise with the real data, you know, it's much more messy. It doesn't obey your assumptions, but you're hoping that the algorithm is robust enough to still capture that structure. I think those two together would be super, super informative for sort of interpreting the result. But they're sort of two separate things, though, sort of cross-validation versus perfect model experiment. But very cool.
Yes. Yeah, very, very good point. Thank you.
Thank you, Chris, for that. That's really interesting point. And we have a question from, or a point perhaps from Gavin in the chat. I was wondering if you want to speak out. If anyone has a question, by all means, please put up your hand.
It was just to comment to Steve Griffey's point. Yeah, I mean, a lot of the VLM changes that you're seeing are indeed anthropogenic, right? They're differently anthropogenic to all the other things that we're talking about, but they are but they are caused by our own activities, mostly groundwater extraction, subsidence, river diversion, building, compaction. And so they change, they have a complex history depending on policy, and they don't have the, if you go forward, they don't have to be linearly extrapolated. They can change too. So, I mean, that was the only point there.
Yes, yeah, that's absolutely true, and that's the basic motivation why we wanted to try to estimate those sources non-linearly in the past, and then think about whether there are actual possibilities of predict that into the future.
Well, it's not really that it's non-linear. I mean, like, I mean, they're not easily modeled by a linear trend, but it's not that they're non-linear in that there are weird, exponential functions or quadratics or anything. They're non-linear because they're a forced signal. They're not a process.
Yeah, but if they are related to, let's say, groundwater depletion or something, we have the hope. I think they are estimates for projections of those components as well. So that's what I want.
But they can change. I mean, so people were,
yes, absolutely.
I mean, people were taking out groundwater from underneath Venice until it was obvious that was causing problem, and then they stopped, and then they started putting it back, right? So so that's a non-linearity, if you like, in the temporal thing, but it's not a non-linear function in the sense that we normally talk about these things, right? It's just
yes, I fully agree,
right?
I fully agree with that. What I meant is that we have the hope that at least some of the processes might be predictable as well independently. Let's say if we have a covariate that describes that reasonable, well, then we could integrate that step by step. Certainly not all processes.
I'm sorry to be nitpicky, but they're like scenarios of the other forcings that we're talking about going into the future. Right.
Yes.
So we are not able to predict what humans are going to do because we're so complicated and irrational. And so we work when we're doing the carbon dioxide emissions, for instance, through a storyline and scenario development type of approach. We don't try and predict exactly what's going to happen with carbon dioxide emissions, right? Or aerosol emissions, right? And the same thing is true for other things that are also going to be affected by policy, right? So we should be thinking more in a scenario of what could possibly happen rather than a probabilistic scenario of what we think is likely to happen.
I fully agree with that. And I don't want to speak against it. So what I wanted to say is really that I absolutely agree. So there are certain processes in VLM that we can't predict because they are dependent on how people behave in the future, right? But there are also other contributions that might be linked to climatic processes, and this is what we want to assess. We want to try to find the forcings for the past, and then think about what that means for the future, and also think about different timescales. In our project, we are primarily interested, let's say, in the next 30 years, and by better understanding the past, we hope that we can plausible predictions for the near future.
Yeah.
So, but that's a really good point, and I absolutely agree.
I mean, my fundamental point, I think, is that the local VLM change is pretty much orthogonal to every other single process that you're looking at, right? And so it's additive and taken. So when we're doing the regional attribution of sea level change, you're better off taking it away and then putting it back in again at the end when you want to make predictions, rather than mixing it all in with the Kalman smoothing and the attribution. It just seems to me that it just adds noise into that system that it's not perfectly designed to deal with. And since it's orthogonal and doesn't really affect anything else, then it's kind of unnecessary.
Okay, thank you.
Anyway, that's fine. Otherwise, everything's great. So thank you very much.
Thank you, Gavin. We have a comment in the chat from Peter saying he likes the scientific illustrations. I presume they're made by your partner or someone in your family. They're wonderful. We have Christopher had his hand up. I'm not sure if it's a new question or perhaps it was for an old one.
Sorry, that's an old hand, and I don't want to hog the airwaves. I do have another question, but if people want to get off or people have other questions, I've already had my time. So
I think no one else has a hand up. Please go ahead, and then as you suggest, perhaps we should close out soon.
So sorry. So should I ask or no?
Yes, please. Yeah.
Yeah. So Sönke, a lot of people in this room, and I know the series in general has a lot of focus on ice. So I wanted to ask an ice question, a question about ancient ice. When you were describing your framework in relation to Carling's earlier framework, you talked about whether contemporary GRD effects are incorporated, how you parameterize ocean dynamics, etc. But one thing you sort of reduce, in a sense, is the representation of GAA. Carling started with 101 models, and you reduced that to 6. And I was just wondering if you could comment upon the nature of that. Specifically, with those 6 models, do you have confidence that you are able to adequately explore the uncertainty space in terms of rheology and ice history and things like that? Yeah, if you could just speak to that.
Yes. Yeah, good point. It's of course integrating more models comes at a computational cost. So at the moment, I'm still playing a little bit around, and the driving factor behind reducing the GIA information to 6 different models has been to focus on the other processes, and by seeing that the GIA was not the most sensitive parameter in the Kalman Smoother framework. So I first used the 161 or what it was as before, and then I changed it to the 5,000 from Caron and others, and it didn't entirely change. So it was not too sensitive. So that's why I decided within this particular run to use previously used GIA model, let's say the ICE5G, ICE6G was in the Lambeck model was in. So estimates that have been very often used by the sea level community as a product. So that was the main driving force. But yes, we should definitely, it's definitely something, it's ongoing, also in terms of including 3D GIA model predictions and seeing how sensitive that reacts to that.
Cool, thank you very much. Thanks for bearing with all my questions.
Yeah.
Thank you. Thanks, Chris, for all your questions. So we're just slightly past noon here, so we should probably be closing off soon. If anyone has any last comments or questions, now is the perfect time. Silence. Okay, wonderful. Yeah, thanks everyone again so much for joining us. Hopefully we see you again next week. Thanks, Sönke, for a fascinating talk. I look forward to uploading it. And yeah, I hope everyone has a great rest of the day.
Yeah, and thank you everyone for coming in.
Cheers. Bye.
Bye-bye.